Welcome to Dynamic Polymorphism with Code Injection and Metaclasses. My name is Cy Brand. I am Microsoft C++ developer advocate. Before I get started on the talk, a bit about what we're doing as Microsoft at CppCon. We have our own expo booth and our room and our table at the expo hall. So please come talk to us about any of the announcements we've been making. And please also take our survey. This helps us to tune our own tools to help you. And you could also win Microsoft Flight Simulator, which is always fun. All right, dynamic polymorphism. What do I mean by this? So polymorphism is the provision of a single interface to entities of different types. And there's a split we're interested in this definition. Dynamic polymorphism versus static polymorphism. Dynamic is at runtime, static is at compile time. Dynamic gives you different behavior based on your dynamic type of an object, whereas static is the static type. I have a cat trying to climb my chair. Hi, this is Milkshake. You gonna say hi, Milkshake? Dynamic polymorphism is typically implemented with inheritance, but there's other ways you can do it. Inheritance is the main method. Static polymorphism is usually implemented with overloading or templates. Now, Louis Dion gave a really fantastic talk a few years back on runtime polymorphism at C++ Now, which I'd highly recommend going to see. There's a lot of overlap with the kind of things we're talking about, and this goes into some more details about part of this session. However, Louis says that we should listen to Sean Parent, not him, so let's go see what Sean Parent has to say. Sean Parent says, inheritance is the base class of evil. This is a talk from 2012, like 8 years ago now, but it's still very much relevant today. And Sean's talk and Louis' talks and other talks which Sean has given, they go into a lot of detail about problems with inheritance. I'm not going to go into so much detail, but you do need to understand some of these concepts in order to really get what I'm trying to get at in this talk. So some problems with inheritance. One is it often requires dynamic allocation where you might not need it. An example is, say we have a base object, and then we have an A and B which derive from it. If we have some function which returns base by value, or we have some vector of bases, then this is going to do what's called slicing, where we take just the base object, part of the object, and we slice off the dynamic part, the part of the derived object. Usually this is not what we want. In order to make this work, we have to do something like a unique pointer. We dynamically allocate, we return a pointer, or we store a pointer in the vector. And there are ways you could get around this by building something on top of inheritance, which does a small buffer optimization or always uses in-place storage, things like that. But by default, inheritance and virtual functions, you need to dynamically allocate if you want to use them in a polymorphic way like this. Another is ownership and nullability. Since we have pointers, we have to care about ownership. We have to care if this thing could be null. If we use unique pointer, then the ownership is clear. But less clear is if this thing is returning a unique pointer, can it return null? Do I have to check? If this thing is taking a unique pointer, what happens if I pass null? Is that valid? What's the behavior? Something we have to care about, which maybe we don't want to. Another is intrusiveness, and that supporting inheritance requires modifying child classes. And an example of this, if we have a base class in mylib, and then we have some other library which has an X class. They both have a doThing method which returns void, and they're virtual. You cannot allocate an instance of otherlib_x and take a pointer to it through a mylib base. This will not work because otherlib_x does not say it inherits from mylib base. This can be a problem. Maybe we can't change otherlib_x. If we could just decorate it and say, oh, we inherit from base, maybe our problem's solved. But maybe we can't. Maybe we don't own the code, or there's some other constraints which stop us from doing this. So polymorphism with inheritance is intrusive. Another is no more value semantics. We have pointers again. If we want value semantics, then we have to build something on top. If we have like a virtual clone function, which will dynamically allocate a pointer and pass it back, which uses the correct dynamic type, then that's a way of getting copy behavior. But you still don't have the usual C++ value semantics, which a lot of code kind of depends on. And similarly, it changes semantics for algorithms and containers. Like if you're doing a sort, suddenly maybe we're sorting on pointers and we have to supply our own custom comparator object. Or if we're storing these things in a set, we might need to do the same thing. So it's another thing we're thinking about where we're not in the usual world of C++ values, which is where we like to be for most of our C++ development. What we're going to do is implement virtual functions by hand. First, we're going to do it in normal C++, which you can write today. And then we're going to improve it using techniques which might be coming in future versions. A lot of the code which I'm showing is kind of complex, and there's a bunch of new stuff and new features, new syntax you might not be familiar with. So I will be glancing over at the Q&A in Remo. So if you have anything you'd like clarified or any questions as I go forward, please just drop them in there, and I will, as long as Remo cooperates, I'll be able to see them and I can pick them up as I go. So this is the class hierarchy I'm going to try and emulate. I'll try and implement by hand. We have an animal class, which has a speak function, which is pure virtual. And we have a virtual destructor. Then we have a cat class and a dog class, which override the speak function and they inherit from animal. Fairly straightforward. Now, how this is implemented under the covers is that if I have a Felix object, which is a cat, then this is going to have a pointer to a Vtable, a virtual table. This virtual table essentially tells us how to call functions, virtual functions in a polymorphic object. So this Vtable will in turn have a pointer to the speak function for cat. So there's a couple of indirections we're going through here when we call speak. We first have to grab the Vtable, then we have to read through the Vtable to get the speak function. That can be a performance bottleneck. This is what I want. Oh my God, I have another cat who is now standing on top of my printer. Hi, do you want to come say hi? I didn't have any cats in my other talk, so you're getting the best. This is Marshmallow, he's very cute. So the cats can speak. This one is not. So this is the interface I want. I want to have an animal class which has a bunch of magic, which I'm gonna implement throughout the talk. And then I have a cat class and a dog class, which both just have speak functions. Note that these are not inheriting from the animal class. I'm just doing all of this with bare C++. But I want to support this use case. I want to be able to create an animal from a cat and call speak, and I want to be able to create an animal from a dog and have it speak and not do any slicing. Okay. So now we'll implement the magic in animal. This is the steps we're going to go through to implement our virtual functions by hand. First, we're going to declare what the Vtable layout looks like for our animal class. Then we're going to fill in the Vtable for our cat and dog class. Then we will, on construction of an animal, we're going to capture the Vtable pointers for the correct concrete type. And then finally, when we call speak or the destructor, we're going to forward our calls through the Vtable. Okay, don't worry if this all seems like a lot. We're going to step through all of these in some detail. Again, this is our hierarchy. Animal can speak, cat and dog override. Let's move on to declaring our Vtable. We're going to start off very simple. Our Vtable is going to have two function pointers, one for speak and one for destroy, which is going to call a destructor of the concrete object. And also, because we're going to be allocating inside our object, it's going to reclaim that memory. These things are taking void pointers because that's how we're going to store our concrete object internally. We're going to pass void pointers around, and then the concrete objects are going to cast those pointers internally. Okay, you'll see how this works in a second. Now we're going to define Vtable for a concrete type. So we're going to have an instance. This is a variable template. We're going to have an instance of a Vtable, and it's going to be templated on the concrete type, i.e. cat or dog. So we need a function which is going to call the correct version of speak, and a function which deletes the object and calls the destructor. And we can use lambdas for this. So for a given concrete object, the first function pointer is just going to static cast to the concrete type and then call speak. And then the destroy function is going to static cast and then call delete. Okay. This all works because lambdas which don't capture can decay to function pointers, which is kind of nice. Okay, hopefully that's all clear. As I said, drop Q&A questions if you have anything you clarified. Next, we need to capture the Vtable pointers. So when we construct an animal class, what we need to do is fill in our pointer for our concrete object and a pointer to our Vtable. So our constructor is going to be a template. It's going to take anything. Of course, in the real world, we would like constrain this, but slideware. And we're going to dynamically allocate a copy of what we're given and store it in concrete. And then we're going to take a pointer to our Vtable and store that inside our animal. Now note that because we have access to what T is at this point, whether it's a cat or a dog. So this is where we're kind of saving this information for later by grabbing the right Vtable pointer and by dynamically allocating a copy of our T. This technique is called type erasure. Finally, we need to forward our calls through the Vtable, which looks like this. Inside our animal class, if we call speak, then we indirect through the Vtable and pass it our void pointer. And remember, that is then going to cast inside the function and call the right version. And then similarly for a destructor, we call destroy. So now we have something which works for that use case. We can have a cat and a dog and speak functions. We can construct a cat. We can construct an animal from a cat and a dog and make them speak, and it all works. This is cool. So let's look at what this has gained us. These are the problems we had with inheritance at the start. And we've solved some of these. We've solved the ownership and nullability because now all our memory allocations are handled inside the animal class. We don't have pointers externally. We're just dealing with the values. We've got rid of the intrusivity because remember, cat and dog did not derive from anything, it just worked. However, we still have the problem with no more value semantics because we can't copy these objects, but we can solve that. We can extend our Vtable with a clone function and a move clone function. And these do roughly what you'd expect. Clone will allocate a copy, move clone will allocate by moving from the object. I'm going to flash up the code for this. It's not that important, it's kind of gnarly. But you can see the third and fourth functions, allocate new and then allocate new and move. I've got a couple of questions. What happens if I pass an object which doesn't contain speak? We're not handling that right now. We would in this slide where we take a type T, we should have some check in there which checks that we have a speak and otherwise gives us a compiler error. So that's how you would do that if you were doing it properly. Then the other question is, shouldn't the destructor also call delete? So the destructor of animal is not going to call delete. The call to delete is inside the implementation of destroy in the Vtable. So this is the destructor for animal, which calls destroy, and the second function pointer here, that has the call to delete. All right. And did I show the definition of the Vtable? The Vtable layout is this one, it has two function pointers. And then this is where we fill in the definition of the Vtable. All right. But yeah, back to where we were. Clone allocates copy, move allocates from moving. Then in our copy constructor and move constructor for animal, we just call through our Vtable to clone and move clone. And we make sure to copy over the Vtable pointer from the object we're created from. And then you would do the same thing for the assignment, the copy assignment and move assignment operators. now we have actually kind of a nice interface. We can create an animal from a cat, we can make it speak, we can reassign it to a dog and make that speak, we can create a new animal from an old one and make that speak, and it all works. We have value semantics, even though we're doing dynamic polymorphism, it's just all handled under the covers, which is really cool. You can even make a vector of these things. Like, because we defined copying and moving and things like that, we can put a cat and a dog in a vector of animals, and this will do what you expect. Great. So we've solved some more of our problems. We've got back our value semantics, and we've got back our normal algorithm and container semantics, as long as we define any of the relevant like comparison operators and things like that for our animal class. The dynamic allocation one, we're not going to solve for a while. That's going to be towards the end of the talk, but we will get to that. A problem is this. This is all the code which I had to write to implement this. It's intentionally small. The point is, it's a lot. Now, of course, you can do a bunch of stuff with macros or clever template magic to make this a lot smaller, and there are libraries which will help you do that, like Dino or Poly. There's a whole host of these things. So you can make this easier, but the point is, I don't want to have to do this for every class which I want to treat dynamically. Okay, it's a lot of work. It's a lot of things to get wrong. And because it's kind of weird code, it's easy to get wrong. So for the rest of the talk, we're going to be improving this with a bunch of features which might be upcoming in C++. The first thing we need in order to do this is static reflection. So reflection is the ability of a program to introspect its own structure and then expose parts of that structure to the rest of the program. Static reflection is therefore the ability to do that at compile time. We do have some reflection capabilities in C++ right now, most of them under the type traits header. So for example, you can check something is an array. This is kind of like reflection, right? You're querying something about the state of your program statically. You're asking questions about your types. It's kind of rudimentary, but it's still a form of reflection. Or something like is same, check if two types are the same. We're querying state about our program. But what about converting an enumerator to a string? Right, that's something people have to do all the time, and we have to invent the wheel every single time we do it. How about iterating over member functions for a type? We can't do that with type traits. We need something more. Fortunately, there is a paper called Scalable Reflection in C++, which solves exactly this problem. And this is, as far as I'm aware, targeting C++ 23. So for an example of converting an enumerator to a string, what we're going to do is we have a toString function which takes some enumerator value. Next, we have some magic. So I'll step through this. Inside this members of call, we have reflects per t. What that does is it reflects on the type t, and it returns an object which represents information about it. Then we have a call to members of, which gives us a range representing the members of that type, which, since t is going to be an enum, this is going to give us all the enumerator values. Like if our enum was color and our enumerators were red, green, yellow, then we'd be looping through the reflection information for red, green, and yellow. Then we're going to check if the value we got for the function is that enumerator value. Is it green? Is it yellow? Is it red? Whatever. If it is, this expr ID changes the reflection information into an actual expression in the C++ world. And if it is the same, then we're going to return the name of that enumerator as a string. Otherwise, we're going to return unnamed, because you can have values of an enum which are outside the range of things which actually have a name. So this is an implementation of enumerators to strings. It's much nicer than pretty much any solution we have in C++ today. Code injection. I have a bunch of things in Slack. I'm just going to make sure my... no, we're good. Okay. Code injection. So code injection is the next thing that we need for improving this. Here we have a class point. Oh, I have a question. Reflection requires being able to modify or program. Introspection is part of reflection. More comment. What's the question? Okay, so I have a class point, which has two members, X and Y. Now, say that I want to have these getter functions. I'm not saying you should use getter functions. This is just an example because people understand what getter functions are. This is kind of a mechanical translation, right? Like I have two members and I want to produce getters for those members, which have the same name prefixed by get and just return the object. So ideally, I could write some code to generate these functions for me. Quickly, I do have a question. I believe we can have enum to string with macros. Sure, you could do that, but this is just a function which you can call, and you don't have to do anything in the declaration of your enum. It's much nicer. So the code would look something like this. We have a const eval block. What const eval means is execute this part of the program at compile time. We then have a call to generate getters, and that's going to inject some code into this context. And we give it the reflection for our type. Okay, now I can show you the definition of generate getters. Looks something like this. Take some meta info. Meta info is the type which reflects or returns. It's the representation of our reflection information. And then we loop over all of the members. If that member is a non-static data member, then we're going to generate a getter for it. All right, looping over the members, generating getters for every non-static data member. Okay, inside generate getter is where the magic is. So there's some interesting syntax here. This underscore fragment thing is not going to be where we end up. It's just a stopgap. But essentially, this is an injection statement. It's going to inject some code into the context which we're currently executing in at compile time. This is a class fragment because it has struct after. You can have class after there as well. It's just it changes the default visibility. So you can have class fragments, you can have namespace fragments, which are injected into a namespace, and you can have block fragments, which are injected into like a function or anywhere you can have just a block of code. So this is the context in which we're injecting. So any code which we inject will turn up here. The question is slide 72, meta is std meta. Yes, that would be std meta members of. So what we want is something like this. We want to inject a function which will look like this. Of course, we want to vary this information based on the reflection information we're given. So I'm going to slowly transform this definition into a general version. So first we have the return type, which is int. We're going to change that into type name, type of member. What this does is type of member gets you this type, and then type name turns that into a C++ world type. Okay. These things are like type name and expr ID. They're called reifiers. They turn some reflection information into C++ constructs. Then this getX, of course, I want this to vary depending on the name of the member. For that, I can use unqual ID, which turns some reflection information into an identifier I can use. And I can prefix it and suffix it, which is what I do here. Then I return the member as an expression. Shafiq has a question. So when is a type considered complete? Can we reflect over the injected members? That's a very good question. So the type is considered complete after all of this has been executed at compile time. So if we're, for example, here we're iterating over all of the members, right? So you can imagine if the type, if we injected something into the type, and we kept on looping all over these members, then we could end up in an infinite loop because we're just injecting things and then reading them. So essentially everything in this const eval block will be executed and all those changes will be made to the class before you can then use it and it's considered complete. All right, so that is our definition of generate getter. So this will change. When we run this program at compile time, it will generate these member functions. So we have written code which has taken reflection information about our program and then generated code for us. Question, what determines the access specifiers of the getters? Would these be private since generate getters appears in the private portion? That it depends on the fragment. So here I have said fragment struct, which means it's going to be public. If I said fragment class, then it would be private. You could also put access specifiers in here. So I could say underscore underscore fragment struct, and then I could put private inside the braces, and that would change the visibility of those getters. Question is, how is injected code stepped in during debug session? So this is an open tooling question. So there are, in the version of the compiler which Lock3 is working on, there are facilities for saying, what code does this generate? Can you print it out for me? Which helps you debug. As far as like what this would look like during debugging, that's a different question, and I don't know the answer to that. And it's certainly an interesting area to look into. Like you could imagine that in the debug information, generated source will be put into there so that when the debugger runs, it will see the generated code and then can display that to you. It would be one way of implementing it. What order do the generators run in? Yes, this will be declaration order. The order of the declarations in my class will be the order in which I iterate over them from the members of call. Right. That's an intro to code injection. Feel free to keep dropping in questions. Now we want to put code injection into dynamic polymorphism to generate all of that massive block of code which I showed, which I don't want to have to write every time. I want to generate that automatically. Right. So here is our original animal type, which had the concrete pointer and the Vtable pointer, and then all the constructors, forwarding functions, things like that. Now I want to make this general, so I'm going to change this into a template. I'm going to call it type class 4 because this is kind of like Haskell type classes or Rust traits. So the changes I made here were, this was my animal. Now it's a template. It takes some template parameter, which I call facade. And the only other change is that instead of a Vtable, the Vtable is now a template, and I give it my facade. Now a facade is going to be a description of the interface for your type. And it's going to look something like this. A facade for an animal is just a declaration for the speak function. This speak function will never be defined. I will never write code for animal facade speak. It's just a declaration. It's like a blank interface which says, here's what an animal should look like. You can think of it as a concept, but instead of defined on usage patterns, it's defined on signatures. And then if I wanted to have my animal class, I would say an animal is a type class for an animal facade. And this should give me all the behavior which I had for my handwritten version. Right, code injected virtual functions. I'm going to follow exactly the same order of operations which I did for when we wrote all of this by hand, but instead we're going to inject this code. First, declaring the Vtable. This was our Vtable, which we had. Now, these last three are going to be the same, but we're not going to be changing these depending on what our type is, but that speak function will, because we might have any number of functions in here. They might have different return types, different parameter types, things like that. What does type class 4 do? Type class 4 is the representation. It's like the the general version of animal, which will work for any facade. Would this add overhead for compiler debug? I'm going to talk about that at the end. So we want to generate this speak function pointer in code. So our Vtable, we have our facade, and we want to generate for every function in the facade, we want to generate a function pointer in our Vtable. So of course, we're going to have a const eval block. We want to do this at compile time. And here's what the magic is. So this for each declared function thing is not a standard thing. It's just a little helper I wrote because I end up having to do this a lot. I don't show the implementation. It's not that interesting, but it just reflects over the facade. And for every declared function in it, it will call this lambda with the function reflection, the return type, and the parameters. It just cleans up the code a lot. So I want to inject a class fragment with that, that function pointer type. And now, similarly to earlier, I'm going to slowly transform this function pointer type into the generic version. So first, we want to change our return type into the type name of the return type for the function which we're reading. We want to change the name to the name of that function. And we also want to inject any additional parameters. So if speak took some other parameters, then they would end up injected in here. The question, does order of compilation matter between where getters are invoked to where they're created? I'm going to come back to that once I finish this train of thought. So this is our generic version of our Vtable. For every function which is declared in the facade, we're going to generate a function pointer. Now we're going to define our Vtable. We want to fill in every pointer in the virtual table with something which does a static cast to the right type and then calls the correct function. So it looks something like this. We're going to inject a block fragment, and we're going to do transformations again. We're going to do unqual ID, which when the question said unqual ID just takes a reflection and gives you its identifier. So if the function was called speak, then this would give you table.speak, like this. Speak, we change it to unqual ID, gives you the name of it as an identifier. Then we are going to use if we have any additional parameters, we inject the types into that lambda declaration, into the signature and the parameters. And we also want to pass those parameters inside the body of the function. Finally, in case the function returns anything, speak returned void, but if something returns an int or whatever, then we need to return. All right. Going to leave this up for just a second because there's a lot of new concepts here and the code looks really weird. But hopefully you can see that the point is you take what you want to generate and you slowly generalize it by taking information from the reflection of your types. All right, capturing the Vtable pointers. This is essentially the same as before. We have to dynamically allocate a copy and we capture the Vtable. The only difference is that we pass our facade as a template parameter to our Vtable, so we know what we're generating for. Question is, what exactly was arrow params? That injects all of the parameter types into here. So if we had a function which took 3 integers, then this is going to add 3 integers into the parameter list for this function. Would you need to add std forward or something to the params pack? Yes, you'd want to use like decal type and forward on the decal type if you were doing it generically. Yeah. Can we generate classes with a virtual function? Oh, that one disappeared. Whoa, suddenly lots of questions. Okay, right, I'm going to work through these in the top. Right, how does the params work? I've already answered that one. Is params a variadic pack or something different? It's, so we'll come back to params back on the screen since there's lots of questions about that. So this ... params, it's not quite a variadic pack. This is expanding. It's kind of like variadic reflection information. This is kind of weird syntax. You know, if this was a variadic pack, then the ... would be after. This is a little bit different. Do fragments require full statements or can they be partial? I think the fragments have to be full statements. You can't have just like random bits of code because what they mean might differ very, very differently depending on the context. Are there any compilers out there that currently support this? Yes, there is an experimental implementation from Lock3 based on Clang, and EDG are also working on a version. Is there some way to view the resulting generated code? Yes, I mentioned that earlier. The Lock3 version lets you print out what code is generated. Do I have to forward the params? Already answered that one. Can we generate classes with a virtual function where the classes are all the combination of all base classes? I'm currently on talk adrenaline and can't parse this question, so I might come back to that at the end. So finally, we have to forward our calls through the Vtable. And I'm not going to dwell on the code here because it's quite complicated and it's mostly following the same patterns we've seen before. We're generating a struct fragment. We're generating a function declaration based on a reflection information and then generating an implementation which forwards a call. You can go look at I have a link to the code later, which you can go look at. I don't want to spend too much time on this. So now we've taken all of that code which we wrote before when we were doing this by hand, and we've changed it into this. We now just say, here's what our facade looks like. And then we give our facade to type class 4, which is going to generate all of that code for us through code injection, and we don't have to do anything else. Question is this stuff being proposed for 23, 26, 29? The static reflection is targeting 23, I believe. Code injection, I'm not sure. I don't have an answer for that one. If someone knows, please drop it in chat. All right. So one thing we could do is, I had this hanging thing left of what about the dynamic allocation? I promised that we would try and deal with this. And we can now that we have a more general facility for generating this information. What we could do is template our type class on some storage policy. And this storage policy will tell us if we want to always dynamically allocate or have a small buffer optimization or always allocate in place, things like that. And then we could also take a policy for how to store the Vtable. Like, do we want to store it remote or inside the class, so that we only have to do one pointer in direction instead of two? These are all options. So some examples of how this could work is I could say, okay, type class for an animal facade. This will give me some reasonable defaults. It might give me a type class for an animal facade where I have remote storage, i.e. I always dynamically allocate the object I'm storing, and I have a remote Vtable, i.e. I have to do 2 pointer leaps for every function call. I could then say, okay, actually I want a type class for animal facade where I have 32 bytes of small buffer optimization storage, and I want to store my Vtable in place. Maybe I just have a couple of functions in my Vtable, and I don't want to pay for that extra pointer leap. I could even say, all right, I want a type class for an animal facade where you store the object in place, so I never dynamically allocate, and if it's too big, then throw a compiler error. And I have parts of my Vtable which are called a lot and parts which aren't. So for the parts which are called a lot, I want to store them in place so I don't have to do 2 pointer leaps. And for everything else, I want to store that off elsewhere, so I'm not paying for too much extra space in my animal object. So this is so flexible. You could do anything here. It's kind of cool. One question is, how settled is this syntax? It's not. the injection code especially is not settled. The most of the reflection stuff is, as far as I'm aware. Would Herb's metaclasses help make the reflective code more readable? I'm so glad you asked, because we're just about to talk about that. Okay, yeah, move on. So this was these were our problems, and we were still left off with the dynamic allocation problem. And I think that we've solved that pretty much as best we can. Like, you're always going to have the problem where if you have an open set of types which you want to support, then you need to have some way of dealing with that, either always allocating or allocating with a small buffer optimization, or storing everything in place and compiler error if something's too big. These are kind of fundamental issues, and I think we're doing about as good as we can do. But we can do better. Someone just asked about metaclasses. What if we could take this code and do this? So this again is some new syntax. This uses type class as a metaclass. So this is saying that animal is some type class, and this will generate an animal class which is equivalent to had we done this. All right. It's a small change, but it's kind of powerful. Like, we're now not just saying that, you know, we have a facade and then we're generating some type class for this thing. We're saying, like, okay, right, animal is a type class. It's like, it's self-documenting in what it means, not like this facade and then using a type class for it. So let's talk about metaclasses. This is a definition from the paper. It's proposed by Herb Sutter. It currently does not have a standard version as targeting, as far as I'm aware. It says, Metaclass functions let programmers write a new kind of efficient abstraction, a user-defined named subset of classes that share common characteristics, such as user-defined rules, defaults, and generated functions. In the case here, I use generated functions. That's the main part I'm using. For example, coming back to our point object, you know, currently point is just an X and a Y. We don't have like comparison object. We don't have comparison operators for it. We haven't defined any constructors or anything like that. You know, some people would use a stood pair instead, because stood pair does all of that. But then, you know, you have to use .first and .second. It's a pain. What we really want is to say, like, point is essentially a stood pair with names. Or more generally, point, I want you to just treat it like a value. I want it to have everything which you might expect from a well-written value type. So maybe we could do this. And by saying, okay, I'm a value, that will define all of your comparison operators, will define constructors for you, and generate all that code without you having to do anything. So value, here we're saying class and value in brackets. What value is a const eval function, which takes some reflection information. This meta info is the same thing we saw earlier. And then inside this function, we're going to have a bunch of injection statements. Now, a cool thing is you could go and read the Metaclasses paper, and I think you should. It's a really interesting paper and has a lot of motivation and great examples. But also, I can pretty much describe it on this slide. If we have a point class, which we use values, it's metaclass, then this is the same as if we copied the definition of point into some hidden namespace and some prototype. You know, we've just taken the whole body of the class and copied the text essentially somewhere else. Then we define our point class, which calls value in a const eval context. All right, I'll go through that again. We have our point class, which uses value as a meta class. We just copy the thing somewhere, and then we call value on that type, which we generated. And this is metaclasses in a slide. Based on all that we learned about static reflection and code injection, this builds upon it and has a kind of simple looking implementation, but gives you a lot of power and expressiveness. So similarly, you would have a type class function, which does the equivalent to everything we wrote in our type class for. And then you would say, okay, I have an animal which uses type class as a metaclass, and now I can have a vector of animals. I can copy them, I can move them, I can pass them around, I can call speak on anything which conforms to this interface. I like this a lot, personally. There are some concerns. One is runtime performance. I'm generating all of this by hand. Based on the experimental compiler that I wrote all this in, sometimes the compiler sees through everything and it all just goes away and it's phenomenal. Other times it does not. Especially because some compilers have been doing a lot of work in devirtualization, like GCC. There will be times that the virtual functions will give you better performance for some use cases. I expect that if techniques like this become more commonplace, then compilers would do their best to optimize those cases. So I don't have too many concerns on runtime performance. Like, there's so much scope for improving runtime performance with things like controlling the dynamic allocation that the compiler optimizations can catch up. Another is compile time performance. The Clang implementation, which I used, is not optimized for compile time performance yet, and I don't want to make any measurements there because it wouldn't be fair. However, the EDG folks have reported that their version gives very good performance, actually, better than some stuff based on metaprogramming. Because, metaprogramming, you end up creating a bunch of types which have to be cached, and then that explodes symbol tables and things like that, whereas this is a little bit different. They can optimize in a different way. So according to the EDG folks, who are probably the people I would maybe trust the most on this kind of thing, then the compile time performance might actually be better than equivalents which we're using today. My kind of more fundamental, philosophical concern with this is it's kind of a new and incompatible way of specifying concepts. Like I said earlier, concepts are based on usage patterns. You say, oh, I can call .speak on this thing. Whereas this version is, oh, well, I have a class which has a speak function, which is subtly different. And it means that, if this became commonplace, then maybe you would want to have some concept which you use at both compile time and runtime. You want to constrain a template by saying, okay, you can pass me anything which conforms to this interface and do it all at compile time. But you might also want to say, oh, I also want to store a vector of these things. Well, with this approach, you would have to implement those concepts twice, once using this facade style and once using the C++20 concept style. I don't have a good answer there. One option would be to actually do something like virtual concepts, which have been proposed before, and just build this implementation or this style of programming into the compiler. Another one would be trying to define some way of reflecting over concepts such that you could generate an interface, but I'm pretty sure that's undecidable. So you might be able to do it for a bunch of cases, but I might be wrong, but it doesn't seem like it would be possible in all cases. So those are some concerns. There's a lot of future work. There's a paper called PFA, which kind of encodes a bunch of what I've been saying in an actual C++ interface, and should be implementable using the experimental compiler. So you can go read that. Some links. The code I wrote for this talk is on Compiler Explorer. I have a slightly different prototype implementation, which implements things a bit different, but it's better commented. And that's on GitHub. You can check out the experimental compiler from Lock 3 on GitLab, and also on Compiler Explorer to play around with it, which is really nice. The Scalable Reflection C++ paper is linked to there, as well as the Metaclasses one. So I'd highly recommend going and checking those out. Finally, like I mentioned at the start, please come talk to us at our expo hall, at the Microsoft table, or our booth, or our exhibitor room. Please do take our survey. You can win Flight Simulator. I hear it's good. I'm terrible at it. We have a bunch of other sessions which you can either check out when the videos come out or later in the conference. This is my third talk so far at the conference. I had one on Monday and one yesterday. And then these are the ones which are later on, some about cross-platform development, code spaces for remote development, and then a new open source fuzzer. With that, I will thank you very much, and I'll take the remainder of the questions. The top question is, there a compiler inside the library allows me to try this? Yes, the lock3 one, go to give it a shot. Does the order of compilation matter between where the getters are invoked to where they are created? And sorry, I just can't understand what this one is getting at. You have the const eval block, which calls the generate getters function. And when that exits, when that const eval block completes, then the code for the getters is going to be generated. I hope that answers it. Feel free to rephrase the question if you'd like. Another question, will compilers provide some switches that allow you to omit pre-processed code? Yeah, like I said, this is an open tooling consideration. Like, you could imagine multiple different ways of doing this. You could have a C++ function which you could call to get the code which is generated and then do whatever you want with that. You could have a compiler switch which emits the generated code. You could have something integrated in your IDE. There's a bunch of different ways you could implement it. And there haven't been any like ways committed to yet, as far as I know. So yeah, there's a bunch of different options there. How does this compare to Rust traits? It's very similar. One key difference is that the implementation I just showed is not opt-in, i.e. anything which satisfies the facade will be accepted. You could implement it in a different way and make it opt-in, either by having a trait which you need to specify, or having some way of mapping from a facade function to the functions in your type. There's a bunch of different options there. That would be a lot closer to Rust's traits. I believe I've seen Herb address concepts for metaclasses in a talk before, and he claimed they're complementary but not overlapping. Yes, the concepts in metaclasses are, but the thing I'm presenting is something which is building on top of metaclasses, and that does overlap with concepts. About the list of 3 concerns you shared, those are concerns about the type 4 experiment you showed us and not concerns about reflection metaclasses. The 3 concerns I shared are these. Yes, so the runtime performance, I'm talking about comparing my implementation versus virtual function calls. So that's not about reflection metaclasses. That's about specifically this. Compile time performance is a bit more general. Like, that would be the compile time performance of code injection and reflection versus methods based on metaprogram that we have today. And then the new and incompatible way of specifying concepts, that again is specific to what I'm presenting here. Is this user class code injection expected to be part of some C++ library, just like Xbind or SB, which use XML to generate code, or remain at the programmer level? So there's a few options. Like, you could imagine that this could be part of the standard library, where you'd have a stud type class, metaclass, which you can use. So that would all live in the standard library. You could also imagine that there's an external library, like you get it off of GitHub and you use someone's type class implementation. So it would live in some library. What's a reasonable path for gradually introducing these techniques into a code base as different pieces of needed machinery enter the standard? So I think for what I'm specifying here, you could do it with just static reflection and code injection, which means that static reflection is going to come before code injection most likely. So when static reflection lands, you'll still not be able to implement this without doing a bunch of other, like macro-based stuff or other template things. So if you were wanting to like do this piecemeal, I'd recommend waiting for static reflection and code injection to land, and then later on you could introduce metaclasses afterwards. Can we generate classes with a virtual function where the classes are all the combination of all base classes? I'm struggling to work out what this means. Is this like you multiply inherit from different facades or something like that? Because you could you could have some way of combining facades, which says, I want a vector of things which are both animals and something else. Like you could come up with a way of composing facades, and that would work fine. If that's not what you meant, feel free to ask another question. Can this support a class that implements multiple virtual interfaces? I think that's fairly similar to what I just answered. When will the drawing for Flight Simulator be done? Every day, at the end of every day, one per day. Will we get cat pictures on Slack? Yes, I can supply cat pictures on Slack. Can I use these techniques to create also test doubles for my classes, using this for like mocking or something? Yeah. I think the mocking is definitely not necessarily of like the dynamic polymorphism thing, but the code injection and reflection are definitely, mocking is definitely a good thing that those could be used for. Yeah. Okay, we've got about 2 minutes left. So right after this session, I do have an Ask Me Anything, so we can pretty much pivot to that right now. So feel free to keep asking me questions about this talk. I'll keep my slides up in case anyone has questions on that, but also feel free to ask me about any of the other talks I gave, or anything about metaclasses in general, or functional style programming in C++, diversity and inclusion, movies, anything. It's Ask Me Anything. One question is, does this get us closer to Python-esque decorators? My memory of Python is I can't remember what decorators in Python do. So if you tell me what decorators in Python do, then I can tell you if this gets us closer. What is the name of the experimental compiler you mentioned? It's under a fork, a Clang fork. So it's GitLab. Actually, I've got my slides open. GitLab.com/lock3/Clang. So as far as I know, it doesn't. I don't know if it has like a product name. It's a Clang fork for metaclasses. Can we ask about your cats? Please do ask about my cats. I have 3 cats. The ones you saw earlier, Milkshake was the tortoise shell, and Marshmallow was the super fluffy golden one. Marshmallow is more like a dog than a cat. He has no idea how to cat. He's useless. And then the third one is called Lexa. She's grumpy. She probably won't come through. She doesn't like people mostly. Is it possible to implement these new language features as a separate source-to-source translation? Sure, I mean, you could do that today, right? Like, there's no reason that you'd have to implement this as a C++ library and language feature. Like, you could write a Python script which does the necessary transformations if you really wanted. The reason this is better is because it would be shipped directly in the compiler, and you could just like include a library and then have access to this this way of doing dynamic polymorphism. So that's the benefit here. Like you can do source-to-source translation of anything. Like you could write a compiler from this to whatever you wanted. It's just a case of making it easier to consume and integrating it into tools and making it more standard across the community.